welcome to lecture number 56. So let me continue with the computation that I had started last time. This was with a view towards proving the associative property of associativity of wedge product as well as the anti-commutativity. So now the main lemma, as it turns out, for proving that is this following a simple looking thing, namely this forms epsilon I that I had defined last time. I have this property epsilon I wedge epsilon j is epsilon ij, where ij is the concatenation of the two multi-indices I and j. Right, so we wanted to check this, and in the process, so we just had to, as usual, these being alternating forms, it's enough to check on basis vectors, their actions on basis vectors. And we had two cases. So we started with since this is both sides are k plus L forms, we started with basis vectors EP1 all the way up to EP plus PK plus L. Of course, here it's we already know that if the degree of the form is more than the dimension, then an alternating form has to vanish. So we might implicitly we are assuming that k plus L less than or equal to n. Otherwise, there's nothing to prove. So we started with k plus L basis vectors EP1, EP k plus L, and we assumed they are ordered in the usual way. And this concatenation, well, right, so there are two cases. The first case, P contains an entry not in I or j. In this case, it turned out both sides are 0. The second case looks rather special, where I am assumed that P contains the entries in this index set P. Together they make up is exactly equal to ij. So in this specific order, P1 up to Pk k plus L is this. Now here, actually, if I want to be consistent, I cannot insist on this strictly increasing ordering, because that does not fit into this concatenation as we observed earlier. So let me drop this condition that this. In fact, I did not use that anywhere. So case 1, but if I drop that condition, then I have to add one more case, which is that case, let me call it case 0. This being the case that P equals P1 Pk plus L as a repeated index. So when there is a repeated index, the right hand side is trivially 0, well, because of the definition, and similarly the left hand side, actually it's you don't even need that definition, specific nature of epsilon, just the fact that they are alternating forms will ensure that if two indices are repeated, you will have two vectors being the same in the input, so therefore both sides will be 0. So this case is kind of clear. case 1 and then case 2. Right. So case 2 I have this. Now there is no conflict. When I write p equals ij, it might very well happen that these indices are not in increasing order. But the point is that yeah, here I should say p equals ij and no index is repeated. So in other words, what I mean is all the entries of P are distinct. Another way of saying that is the entries of I and the entries of J, there is no common entry in between these two. Right. So and then once just evaluates both sides. So epsilon ijk. So in this case, when I evaluate it on P, I get 1 by definition of epsilon ij. Now the left hand side is we have to go to the definition of the wedge product and then you expand it out like this. This was where we had stopped last time. Well, let's look at these terms in the sum. The only way a term can be non-zero is that the permutation sigma will have to be a permutation which takes the indices 1 up to k back to the same set 1 to k. Otherwise, if sigma takes one of these indices here, if sigma takes any of these indices to something other than 1 to k, something in other words more than k, then epsilon of I acting on that will be 0 for the simple reason that if you see this P1 is I1, Pk is Ik. So we know that epsilon I acting on certain basis vectors will be non-zero if and only if the basis vectors involved in the inputs are permutations are just EI1, EI2, EIK in some written in possibly different orders, but essentially the index set has to be from this set I1 up to Ik. In terms of P, the index set has to be from P1 up to Pk. So essentially the sigma 1, sigma k has to be one permutation of 1 to k, and likewise sigma should take the index set k plus 1 etc. back to k plus l. So a term in the sum is non-zero only if the sigma of 1 etc. sigma k, this set should be the same as 1 to k, and sigma k plus 1, sigma k plus l should be the same as k plus 1, k plus l as sets. So therefore what we can do is therefore we can write sigma equals tau times eta, where tau is belongs to Sk, permutation on only k letters, and eta belongs to permutation only on L letters. So it's quite clear what tau and sigma have to be. I mean it's essentially, so for instance, tau is a permutation defined by 1, tau 1 equal to sigma 1, tau k equal to sigma k, and tau k plus 1 onwards, nothing happens. K plus 1, tau k plus L equal to k plus L. Similarly, eta 1 equal to 1, etc. So eta doesn't do anything to the first k and then permutes all this. And this even though both tau and sigma, actually the way I've written it, they act on k plus L, both of them act on k plus L symbols. Since they're not doing anything, the tau is not doing anything to the last L letters. Tau can be regarded as an element of Sk and eta can be regarded as an element of Sl. Now, right, and in fact, once we have this, of course, we know that signature is multiplicative. Also, we have the sign, sorry, not signature, the sign of a permutation as a behaves well under multiplication, composition of permutations. So I have this. And another small change I make is the way I've written it, eta instead of, notice that this for k plus 1 onwards, I can think of, instead of eta acting on 1 k plus 1 k plus L, I can just think of eta as a permutation of regard eta as a permutation of 1 to L, in which case this, for instance, what I have here, what I was trying to write here, this stuff will become like essentially sigma of k plus 1 will be k plus eta of 1, sigma of k plus L will be sigma of L. The point being that anything in between k and k plus L will be of the form k plus something. What is changing is that something. So I might as well regard eta as a permutation of the various things that you add to k, which is what I've written here. The advantage of doing that is, now what we can write, this is the quantity we are interested in, EP1, EP k plus L is, I still have that 1 over k factorial, L factorial. Now I have tau in Sk, eta in Sl. The original sum was over Sk plus L. So, but we saw that the original sum contains lots of zero elements. Any permutation which does not have this property will give rise to a zero term. So we just have to worry about those permutations, those elements of Sk plus L for which this holds. And once we restrict to those permutations in the sum, I can write it like what I'm doing now. So tau in Sk, eta in Sl, and then I use the multiplicative nature of sine, then E tau 1, E tau k, and then times epsilon j. Then I'll use this as well. E, oops, I forgot the P. P tau 1, P tau k, and here I'll have E p k plus eta 1, E p k plus eta L, and so I split it into, the point is that I can write it as a product k 1 over k factorial summation over tau and sk sine tau, then I just keep the epsilon I, EP tau 1, EP tau k. This is one term, and the other one is 1 over L factorial eta in SL sine eta epsilon j E p plus p k plus tau 1, etc. Oh, not tau, it's now eta. P k plus eta of L, and one whole and a big bracket around this. And this thing that I have, the first term is by definition alt epsilon I acting on, well, yeah, E1, rather EP1, EP1, EPK, and then the second term similarly is alt epsilon j acting on E p plus p k plus 1 p k plus L. Which is just, I mean, since epsilon I is already alternating, alt does not do anything to it. This is 1, and likewise the second term is also 1. The way, because of the fact that P, assumption that P is a concatenation of these two index sets. Both these terms will give me 1, and therefore 1 is done. Now the last case, so the third and last case is P is a permutation of ij and has no repeated indices or entries. Right. So these are, I mean, this third possibility exhausts all the things that can happen. So we just, and how do we deal with this case? Well, in this case, we can apply a permutation of P which gets us back to case 3, case 2. So if P is a permutation of ij, in other words, so P in our notation, I'm assuming that P is ij sigma. So in that case, what we can just apply sigma inverse, for example. P sigma inverse is ij, and then sigma multiplied by sigma inverse, which would be 1. So P sigma inverse would be ij. So then what one would do is, one would start with this, as in the proof of case 2, except that you will start with P sigma inverse and then you verify the formula. But then you notice that P sigma inverse, if you have it, if you have both sides equal, the final point of final object of interest is this equation. If both sides evaluated on P sigma inverse are the same, then both sides evaluated on P itself will be the same, because you can go back to this just by moving things around. In other words, applying the reverse permutation, we can apply permutation of P, which gets us back to case 2. The effect of the permutation will be to multiply both sides by the same sign. So this is essentially reduces to case 3, case 2. So that completes the proof of this. Now I should remark, perhaps I should have remarked this on this earlier, but this proof, this exposition, I'm more or less following exactly as it's presented in John Lee's text, Introduction to Smooth Manifolds. So I should say reference John Lee, Introduction to Smooth Manifolds. Right. So now, so once we have this lemma, then we can move on to the main object, the theorem of main interest for us. So now, so we wanted to prove associativity. So I have omega AKV eta in ALV and let's say alpha in ARV. So one wanted to check that this is equal to this. Now what we can do is, with all that we have discussed so far, we know that we have a nice basis for this AKV, ALV and ARV. As fix a basis omega 1 omega n of V star, the dual space. Then we have basis for AKV etc. given by epsilon I dot dot. So the length of the index dictated by what this the degree of the form one is considering, but we are using the same notation epsilon. The index set will keep track of the degree. Well, once we have basis for all these spaces, since the wedge product is itself multilinear, i.e. so we have this was the first property that I wrote down, the bilinearity of the wedge product, but here actually we have three forms, but it doesn't it's the same thing carries over. So and one can conclude that since the wedge product is multilinear, so let's call this equation as star. It is enough to verify star for the basis forms. So what one does is you expand omega in terms of the epsilon I, eta in terms of the epsilon j, and alpha in terms of the epsilon k, where I, j, k are multi-indices. Expand them, in other words, write them as linear combinations, then use the multilinearity of this wedge product, and you will end up with a whole bunch of terms. And the individual terms in the sum will be of the form of this form on the left side. On the right side, they'll involve terms of the form so these terms will occur in the left side and the right side with the same coefficients, but we want to know if this form is actually equal to this, i.e. enough to show this. But this thing here on the left side is, we have seen that this is same as ij wedge ek, which is the same as epsilon ijk, and it's also the similarly right side as epsilon I wedge ejk, which is equal to epsilon ijk. So both sides are the same. Therefore, this star holds. So it's a pretty straightforward consequence of this. Now, the other thing is anti-commutativity. Here, I should remark that it's first let me write down the formula. So one is interested in showing that omega wedge eta is -1 raised to KL eta wedge omega. Yeah, here I should remark that when we are dealing with tensor products, associativity is extremely straightforward. There's nothing, I mean, it's almost it's a triviality from the definition. Here it's not so obvious because the alt map is involved, which involves a sum and so on. On the other hand, when one is dealing with tensor products, omega tensor eta has absolutely no connection with eta tensor omega. The two are not related at all. So no such equation holds. Here, interestingly, there is an equation relating omega with eta and eta wedge omega. They justify by sign, in fact. So again, we can use our basis to write omega in terms of the epsilon I, eta in terms of the epsilon j, and enough to show by the same logic, we'll end up with same coefficients. Epsilon I wedge epsilon j equals -1 to the power k. This. So I'll just write this and then stop. So EI, yeah. So enough to show this. So I'll stop at this point. Next time I'll complete the small calculation. Bulk of the work has been done. So I'll finish this and then that will complete our discussion of multilinear algebra, tensors and forms, alternating forms on vector spaces. Then we'll carry over these constructions to manifolds. Thank you.